thank you very much for hosting us to this event, to Toby here, and also to Hardware Mask. Alright, so Industry 4.0. I was working for ABB before, here in Shanghai, before I started my company, and we had this interesting conversation. I'm not trying to lecture you about the Industrial Revolution or anything, so you can look this up on the internet by yourself. But we had this interesting conversation once, a discussion even, like what should we call it? Should we call it the fourth industrial revolution or rather Industry 4.0? So if you look back in history, you have the first to the third industrial revolution, all with different focus points. And since the 1960s, industrial robots were introduced in manufacturing. In fact, in 1961, the first robot was introduced in a GM factory in the US. So this was sort of like the starting point of the third industrial revolution. But now, since 2012, people speak about Industry 4.0, which was something that was started by German scientists, some kind of meeting. Well, the point really is, should we now call it fourth industrial revolution or Industry 4.0? And the difference between here is that, like, before, technology was implemented in the industry and then it transformed societies. But now, society is already transformed to the internet and so on. And now, in Industry 4.0, the goal is sort of to connect everything in the factory, create a big network, put all the machines together with sensors and whatnot, put a control system on top, basically put the internet into the factory. So it comes actually from the outside. That's not something that comes from the factory or from manufacturing itself. So, in the end, at ABB, when we had this discussion, we decided it should probably be called Industry 4.0 rather than the fourth industrial revolution, since it's coming to the factory and not the other way around like before. Well, Industry 4.0 has four design principles. Like I said, I will not lecture you on this, but I will show you something about technical assistance and about decentralized decisions. Technical assistance. What you probably have seen on the internet or on YouTube, on TV or somewhere else, when you think about automation, road automation, you probably look at something like this. But then there are new type of robots that are used, which are called collaborative robots. You can see over here. Those are sort of cute little assistants for any manufacturing process. Yeah, and the reason why these were introduced is, I think, very well explained using this sort of spectrum. So when you look at, oops, I'm sorry. Okay. You have productivity and lot size, of course. So you have this is very large. You want to introduce automation with robots. They do the same process over and over again, but they're not very flexible. Like on the other end of the spectrum, you have manual labor, super flexible, but you can only produce very little. So the industry thought we need to put something new in there, right in between, and this is where collaborative robots come into play. So it's human flexibility and ingenuity, plus the high repeatability and reliability of robots combined, and all that in a very safe way. So this collaborative robots, you can work with them directly together. They will not hurt you, they will not harm you, they will actually react to what you do with them. Here are some examples. They come in different sizes. Most of them are very small, like most of them are very small. They're just a little bit longer than a human arm normally. But then there are also some which are very large, and this is where technical assistance in its origin sort of comes into play. The very original idea of technical assistance is actually nothing new. I think it was also in a GM plant in the 90s where they installed cranes, overhead cranes that are in the factory we still have there, just for the purpose to help the worker to do a certain task, especially when the object is very heavy. So you have a robot where you have this strange machine that will help you to lift something heavy. Now, of course, these robots, this is a standard industrial robot from the old design, basically. Just with the green soft padding, so it will be more safe. So when it hits you, it doesn't hurt so bad. but it's still designed for technical assistance. So for helping the worker lifting something heavy, for example. As you can see in this picture over here. So you have those two things. You have technical assistant robots, which is something new in the way that it's conceived right now. It's presented in the factory. Basically, large robots that help the worker to lift heavy objects, or most of the time I would say heavy objects. Or you have the small assembly robots, the collaborative robots on this side. Here, two examples from KUKA and ABB. Probably the most biggest companies in this field. But then, of course, these are just machines that you put in the factory, and they need to be a very good machine. They can very flexible. They can be used in many different ways. But then, of course, on a bigger level, it's about the factory. It's how does that look like, the factory of the future, and what does it mean really in the context of Industry 4.0. So you have decentralized task control. So it means every robot or a couple of robots together, they will perform a task together. They can probably react to changes in this task. They can react to a human being walking into the task, or can react to changes in the object, or changes in position, and so on. Then you have centralized control, the overall factory control, which is basically just telling you, okay, we need this many parts, and you send the command out to all the robot cells. And lots of sensors will be implemented to just understand the condition, for example, of your machinery. Could be robots, could be motors, all kinds of machinery equipment that you use, or conveyor belts. For condition monitoring, that is actually a very big topic. And even ABB is working in one of the last projects I was working on with ABB. Factories today, robot automation today looks very much like this. In the automotive industry, here, a welding application, and over here an assembly application. Then you have pick and place, material handling in this part. So this is what the reality currently has. But what's also here is actually there are no human workers. In most of those cases, everything is completely automated. So now let me build the bridge to my startup. So with the increase of automation, increase of robots, which is currently happening, also because of China, we believe at Motus Operandi that the energy consumption of those robots, of all this machinery, will be extensive. In the area of, if you take the robot market from today, it will be very large. So and it's not. So this is what the problem is really. It's in a very simple way. It's the electricity is consumed by a completely automated factory. All the motorized machinery, not just robots, but also conveyor belts, all kind of transportation systems, other motors, depending on what factory, what they are producing, and so on. So the electricity consumption, this is something that we are concerned with at Motus Operandi, especially when it comes to robot automation. So this is the latest projections of the robot market. In fact, I'm not sure you can actually see that well. In 2013, over here, the operational volume of all robots worldwide was 1.3 million robots. And in 2019, it's predicted to become 2.6, so it will double. Just to put this into perspective. So I just said before, in 1961, the first robot was actually implemented at a genuine plant. That was 52 years ago compared to 2013. So it took 52 years to have 1.3 million robots operational, and now it is 7 years where this number will double. And then, of course, you have a very extensive electricity bill for these type of electrical actuated robots. So to give you an idea, one robot in a highly automated plant for manufacturing cars, a welding robot, like in this application here, for the car body, we estimate that one robot operating one day would in the area of $20 to $50 every day. That's just the consumption of the electricity of one of those rather large robots. So we believe that environmental awareness and automation is not necessarily something that are opposing forces. So it's that's what our vision sort of is, and our magic is very simple, very easily explained. So the way robots operate today are based on geometry. So you have this robot arm moving this object from A to B simply, and all the options that you have in order to do that is basically a straight line, which sounds intuitive to everybody. Straight line seems to be the best path to take for a robot or for an object, but this is actually only true if that object was self-driven. So if that object would move by itself, but it's actually moved by the robot arm, and the robot arm is nothing different from a human arm. And if you think about it, when do you ever move anything in a straight line? So this is our initial realization that we had. So what we are having with our magic is that we are implementing human-like motion into robot arms, and that allows us to save energy in the same, keeping the same level of productivity. So I have a short demo here. This is a simulation from a real robot platform. It's a material handling platform. So in this case you have this robot arm in the center of two other machines. So the green point symbolizes one machine and the orange point is the second machine. Over here is the starting point, so the robot will pick up a part, put it into machine, into the green machine, then putting it into the yellow machine, and then over here we'll drop the object and then we'll go back to the start. And on the left side you see our movement, our motion that we can do, and then here is the standard approach. And over here you see the energy consumption over the whole period with 30 seconds. I just realized here they're wrong. It needs to be the other way around, but it doesn't really matter. So now what you see, normally, the robot is putting the object into machine 1, and then the machine has to process the part, so the robot needs to wait. And normally you don't consider this as something that you need to program. You just put the part in and you wait. Done. So the robot is not doing anything for 6 seconds. But it actually does something. It actually consumes electricity. It's just sitting there stretched out, and you should do something better than just having it in this direction. So what we do in this case, the robot is going up into an equilibrium position where it consumes almost zero energy, which you can see here. At this very point, it's almost zero. It's not completely zero, of course, but it's a very low level of energy. So for this whole application, we keep the same productivity, evidently, and we can save up to 30% energy just like that, implementing different motion. Alright, our business model that we anticipate is one is consulting service. So if you have, just like in this case, this was on an existing platform already, so we can just go there without additional hardware. We just reprogram the robot in its motion, and in the end it will be more energy efficient. This can be done throughout consulting service, so we just go there, we plug in our computer, we reprogram the robot, and we leave, and then everything runs more energy efficient. That's consultant service. This second business model that we anticipate is to put our technology directly into robots, so that robots will actually be able to have this kind of feature instead of just making straight lines. It has the human-like motion feature integrated directly into the robot. So a quick summary. So I was just in the beginning talking about the Industry 4.0 and how it's better to call it Industry 4.0 instead of the fourth industrial revolution. One part of Industry 4.0 is the emergence of new type of robots. Collaborative robots for assembly, for collaborative assembly. And then, my robot startup, which is about energy consumption of industrial robots in a fast-growing robot market. Thank you very much.